Well, good morning. We are going to continue our study of inferential statistics, focusing on hypothesis test number 3, which we're going to call the repeated measures design. Repeated measures design. Now, there's actually a t-test associated with this, but before we get into that, we need to introduce some concepts and see how we really approach this. We are delving back into the world of the experiment, and we remember what experiments are, right? We're manipulating an independent variable, measuring for its effect on the dependent variable, right? We're administering some treatment, and we're seeing if it has some effect. Okay, so this is an experimental design. In which the same subject is observed under more than one measurement. The same subject is observed under more than one measurement. What do we mean by that? Well, we have this thing called the pretest. And of course, we have one group of subjects. Let's pretend we have 8 subjects, n equals 8. We have this thing called the pretest, which is actually the first measurement. Some people consider it the baseline measurement. It's the very first measurement. And so we have, all these pretest scores. And then we introduce some treatment, and then we measure them again. This is called the post-test. The second measurement. So we have a whole set of post-test scores. Subject number 1 weighed 186 pounds, went through the 12-week health and wellness program, weighed out at 176 pounds for a difference of 10. So we have another column that we call difference. The difference column. This minus this equals this. And this difference column is considered the effect. In that particular case, there was a reduction of 10 pounds. And so we infer that the treatment caused that. So we have this whole set of difference scores. We say that the subjects serve as their own controls. The subjects serve as their own controls. What do we mean by that? Well, we know what a control group is in the experimental sense. Remember back from our first section, that control group was the group that gets no treatment, and then the experimental groups are compared to it, and so on. This concept is very similar. The subjects serve as their own controls. Okay? The same subject measured on the pretest is also measured on the post-test. Okay? So any difference that we might obtain, we can attribute to the introduction of the experimental treatment. This is thought of as the subjects serving as their own controls. Again, the same subject measured on the pretest is also measured on the post-test. So any effect that we might detect, any difference that we might detect, we attribute to the introduction of the experimental treatment. Another way of saying this is we statistically remove the effects with an E, of course, as in cause and effect. We statistically remove the effects of the individual differences between subjects. We statistically remove the effects of the individual differences between subjects. That's a little bit of fancier way of just stating the subjects serve as their own controls. And again, we have this pretest, so we have a pretest mean. We're going to call this x bar sub pre, simply the sum of the pretest scores divided by the number of scores. We also have an x bar sub post, simply the sum of the post-test scores divided by the number of scores. And we have this new entity called d bar, the mean difference. Now we know what x bar is, sample mean. Now we're going to be working with this entity called d bar, which is simply the sum of the difference column divided by the number of scores. D bar. Now this is where things are going to change a little bit. This is where things are going to change a little bit. We're actually now in hypothesis test number 3, we're working in a new sampling distribution. Our sampling distribution changes. The central limit theorem, of course, remains the same, but the sampling distribution changes a little bit. Where before, in hypothesis test 1 and 2, if you guys remember, we were working in that sampling distribution of the mean, right? What were we doing? We were equating x bar to mu, weren't we? In other words, if you guys remember, in every single example that we worked on, I would always state, where does this individual sample mean fall on the sampling distribution of the mean? Oh, if it falls in the tails, the distance from mu is large enough to be deemed, see, remember that? Remember that, all that stuff? What I was doing was equating x bar to mu. Where does this individual sample mean fall in relation to mu, right? That's what we were doing. Now things change a little bit, but they stay the same, just in a different form. Now instead of equating x bar to mu, we're going to be equating d bar. We're going to be working with this mean difference, and we're going to be equating it to mu sub d bar. Oh, we got some new stuff here. Let's talk about this. We have a new sampling distribution. It's called the sampling distribution of differences between means. It's called the sampling distribution of differences between means. Where before, in the z-test and the one-sample t, where before we had a sampling distribution of an infinite amount of x bars, remember? An infinite amount of sample means clustered around mu. Now we have a sampling distribution of differences. Each one of these little infinite amount of data points, each one of these infinite amount of mean data points, instead of being an x bar, it's now a d bar. we have a sampling distribution of differences between means. The mean of the mean differences we're going to call mu sub d bar. Mu sub d bar. The mean of the mean differences. We're now working in a sampling distribution of differences between means. Normally distributed, right? Per the central limit theorem. The mean of the means equals the population mean difference. And the dispersion of all these mean differences around the midpoint we call the standard error of the difference. The standard error of the difference. The standard error of the difference. So instead of the standard error of the mean, like we worked with before, we're now working with this standard error of the difference. We symbolize it using an S subscript d bar, the standard error of the difference. It's actually equal to the standard deviation of this difference column of scores divided by the square root of the sample size. The standard error of the difference is simply the dispersion of all these little infinite amount of mean differences around the mean of the mean difference. So what the standard error of the mean was in number 1 and 2 to that sampling distribution of the mean, the standard error of the difference is to this new sampling distribution of differences between means. All we're doing here is trying to figure out where this individual d bar falls in relation to mu sub d bar. Class, I have a question for you. If the d bar that we compute, once we start doing examples, you will see this, but if our particular d bar falls about right here on the sampling distribution, what's our decision going to be? 7. Yeah. On the other hand, if the particular d bar we compute actually falls way over here, or perhaps way over here, what's our decision going to be? Reject. Same drill. Different research question. Remember, there's a specific hypothesis test designed to fit any research question out there. This one is experimental. This one asks the question, did this cause the changes in this? Is there a significant difference between the pre-test and the post-test? You know, did the weight loss program have a significant effect at reducing the overall weight of the subjects? You know, did the behavioral intervention program have a significant effect at improving positive behaviors in our sample of subjects? You know, did the treatment have a significant effect at doing, you know, whatever it was designed to do? That's an experiment. That's, you know, it's as simple as it gets. Now I said, you know, I introduced this section as the repeated measures design. And I actually told you, if you remember, you know, there's a t-test associated with this. There are actually a number of repeated measures designs out there in the scientific world, you know, where we're measuring one set of subjects, you know, twice or perhaps, you know, many, many times. But in this particular case, you know, considering this is an introductory stat course, there's a t-test associated with this. It's called a correlated t-test. Our t-statistic is equal to d bar divided by S sub d bar. Mean difference divided by standard error of the difference. Mean difference divided by standard error of the difference. Now, if you remember the formulas from Z and the one sample t, what were we doing? What were those numerators? They were all mean differences, weren't they? Remember x bar minus mu? Yeah. How about those denominators? What were they? Standard error of the mean, right? Mean difference over error estimate. Same thing, different form. Mean difference over error estimate. This is, of course, this. This denominator is this. And computationally, what does this ask of us? It asks us to compute a standard deviation of this difference column of scores. So it actually tells us to compute an S on this column of scores. So this S subscript D is just simply the standard deviation of the difference column of scores. Now, what were those standard error of the mean? Remember those? S over the square root of n, remember that? Or sigma over the square root of n? Well, same thing. S, as it relates to the differences, over the square root of n. We have this hypothesis test called the correlated t-test. It has a couple other names. Don't ask me why, it just does. I didn't invent this stuff, okay? This correlated t-test is also called a paired t-test. It's also called the dependent sample t-test. This analysis actually have three names, and they're all the same. I mean, it all means the same thing. It's called the correlated t-test because the pretest and the posttest are correlated. I mean, you could actually consider this x and you could consider this y. You know, so we have a relationship going on here. The pretest and the posttest are relate. Why? Because they're the same subjects. The only difference between this and this is this. And that's recorded in this column. That's a difference. This minus this is this. So the only difference between this and this is actually this. It's called the paired t because we're working with pairs of scores, right? And it's called the dependent sample t-test because we have a dependence relationship. And we need to, this is actually a scientific term. I just want to talk about this for a little bit. Dependence. From now on, whenever you hear the term dependence, I mean in the scientific sense, it means relationship. Okay? Think about relationships. You know, what's actually happening in a relationship? You're dependent on each other. You know, think about, you know, your relationship with your parents, or your, you know, relationship with your significant other, your husband or your wife, or there's dependence there. Okay?
Sorry,
yeah.
Laura Garcia, I'm sorry, not Garcia.
What? Lorena Garcia?
Yes, that's it.
Yeah. Yeah.
So we have, you know, this dependence relationship. You know, so, you know, dependence implies relationship. Okay? Independence implies no relationship. So in the scientific sense, whenever you hear the word independence, you know, there's no relationship. Think of like not being in a relationship. What is happening? You're independent of each other. Okay? So this t-test actually has three different names, and on our next exam I will tell you that, you know, you have to remember that there's, you know, three different names. The correlated t-test. You know, essentially, you know, where does this individual mean difference fall on the sampling distribution of mean differences? If it falls in the middle somewhere, the distance from mu isn't deemed large enough to be deemed significantly large enough. If it falls in one of the tails, that distance from mu is considered large enough to be deemed significantly large enough. This is information out of chapter 10. On your syllabus, if you look really closely, you will see example 10-12, just right on your syllabus here. Look at that example. This is going to be a little preview for what we're doing next class. Okay. Next class, we're going to start into some examples. The purpose of this talk, this really short talk, was just to introduce you to the basics of this concept. When we come back next session, we're actually going to do many, many examples of this particular repeated measures design using the correlated t-test, which actually has 2 more names. And this concludes this particular session. Thank you.